On to the next one. We have Ben Smith here.
Hi,
Uh,
Nicholas.
Hi, Ben. Ben, well, I shouldn't need to read what you are doing. We have regular meetings. You independent lunar settlement specialist and working on the lunarhomestead.org. Do visit that because it's a treasure trove of information. Ben has been collecting information about what you need to establish a settlement on the moon for quite a while.
Slight correction. .com.
Sorry,
Okay.
.com was
I'm not sure where .org will send you. So
probably not.
yeah.
You might register that too, just to have a forwarding link. But
I
yeah,
have it, but I haven't done anything with it.
uh,
It
.com.
may forward you. That's fine.
Yeah. Okay. Anyway, that's that. I'm not gonna keep you any longer. So
Yeah. Let me go
floor is
ahead
yours.
and get this thing going. All right. Everybody see that?
Yes.
Good. All right. Hi, everyone. I'm Ben Smith, a lunar settlement scientist and founder of Lunar Homestead. And Lunar Homestead is researching the frontier enabling technology and techniques needed for permanent and sustainable lunar settlements. And today I'm going to talk about the one standard lunar homestead atmosphere. So, the most critical feature of a lunar homestead or any space settlement is the pressure hull that can safely and effectively contain the atmosphere of the habitat. Uh, no habitable pressurized atmosphere equals no people, equals no settlement. So, we need to decide on what that atmosphere is before we can start designing the actual habitats and equipment. So a one standard atmosphere is a measurement of atmospheric pressure. One SA is 101.325 kilopascals or 14.7 psi. And this is the pressure of Earth's atmosphere at sea level minus the water vapor. And it's the maximum that we should need for any off-Earth habitat. Most of the air-breathing life on this planet is well adapted to this atmosphere, and this would be the best choice for maximizing homesteaders' health and comfort. But one SA is a measurement of pressure only and technically doesn't include the gas composition. However, space settlements must include gas composition in their life support design. So Earth's atmosphere is composed of 78% nitrogen, 21% oxygen, and the rest is a mixture of trace gases like carbon dioxide. So this would be a one standard Earth atmosphere and would be considered the gold standard of habitat atmospheres. However, there is a high price to pay for this luxury. Lunar homesteaders and really anyone living off planet is going to need a different atmosphere. And the rest of this presentation will explain why. But for right now, I'm going to cut to the chase and give you the one standard lunar homestead atmosphere. It's a 78% nitrogen, 21% oxygen mix at 70.11 kPa. And this is the equivalent to 3,000 meters of elevation, or about the elevation of Quito, Ecuador. And we could use La Paz, Bolivia at 3,700 meters elevation to make it 64 kPa. But I've been to Quito and I know from experience that 70 kPa is more than adequate. So there are four primary drivers we need to consider in deciding on an ideal atmospheric pressure and composition for space settlements. Not only does our breathing gas have to keep our homesteaders alive, but it must also keep them comfortable and safe indefinitely throughout their entire lifespan. This includes pregnancy, children, adulthood, old age, the whole thing. Settlement requirements are significantly different than outpost requirements. We can get away with different atmospheric composition and pressure if you're only going to live there for a couple of months and then be rotated back to Earth. In addition to the health of the homesteaders, the other major safety concern is fire. Fire in an enclosed, pressurized space is something to be avoided at all costs. Changes to oxygen partial pressure and concentration have a direct impact on the flammability of everything in the habitat. So the composition and pressure of our habitat atmosphere is critical in determining fire safety. Lunar homesteaders will have plenty of oxygen once mining and refining operations are underway. Nitrogen, or any other physiologically inert buffer gas, is a challenge, however. Decisions made now will have a direct impact on the initial and ongoing expenses of every settlement, as well as to their sustainability and their vulnerability. And I was going to briefly touch on a few of the engineering challenges, but this presentation was already getting too long, so I cut it. But let's just say that figuring out how the breathing gas component of a sustainable life support system using a one standard Earth atmosphere is hard enough. We know what to expect from this breathing gas. Changing the gas composition and pressure means we'll have to design new equipment and figure out how all that equipment and life forms and material operate inside this new exotic atmosphere. And we have to figure out how they operate over a long period of time. So any exotic atmosphere is going to require a substantial investment in research and time. Let's start with the human needs first and look at the most commonly used atmospheres. All right, let's take the bare minimum. According to NASA, the minimum allowed oxygen partial pressure is 24.82 kPa, which is 3.6 psi, for 100% oxygen atmosphere. Now, no mission has ever flown with this atmosphere. It's considered the absolute minimum to only be used for short periods of time in emergencies. And there are absolutely no physiological advantages for this gas mix and pressure. It's purely logistical. And mostly because it doesn't use any buffer gas, which we'll get into later. There's some engineering makes it easier, but it also makes the engineering harder. So it's about a wash for the engineering requirements. But there are significant short-term health issues involved with breathing this gas. And in fact, NASA limits the crew exposure to this oxygen partial pressure to 12 hours. Basically just enough time to hopefully fix whatever problem occurred. And in addition, this atmosphere leaves no margin for error. The minimum alveolar oxygen partial pressure is 13.73 kPa. Less than that, and your lungs simply won't absorb enough oxygen to function properly. And so that's an 11.09 kPa difference, which just doesn't leave much time to fix a leak or to get out of the habitat or to deal with whatever issue is causing a pressure loss. So next we have a 100% oxygen atmosphere at 34.47 kPa or 5 psi. And this is many people's favorite atmosphere and is often talked about for lunar settlements. It's what NASA used for all the missions before the space shuttle. So Mercury, Gemini, Apollo. And it definitely worked for those missions. The primary reason for its popularity are its simplified engineering, its weight savings, and there's a little more protection against sudden decompression. Crew comfort was maybe a distant fourth, and the missions were short anyway. And honestly, it was figured that the astronauts were tough guys and they could just suck it up and deal with any difficulties they experienced. However, settlers breathing this atmosphere are going to run into problems pretty quickly. There haven't been any long-term studies using this atmosphere, but even relatively short exposures can cause a lot of problems. And even NASA states that crew exposure to this atmosphere should be limited to 14 days. And here's a list of just some of the potential problems. There's many more. And like I said, we don't even know what the long-term exposure of this is. And one study I found showed that chicken embryos had development issues when exposed to 100% oxygen at 20 kPa. And yeah, that's 15 kPa less than the 35, but I'm not sure our settlers are going to want to bet the health of their children on a difference of 15 kPa. Human reproduction is going to have a hard enough challenge dealing with lunar gravity, we don't need to add the habitat's atmosphere into the mix. And then there's Skylab's atmosphere. 74% oxygen, 26% nitrogen at 34.4 kPa or 5 psi. And this atmosphere should take care of a lot of the problems of a 100% oxygen atmosphere, at least for the short term. But again, we have no long-term data for it. The longest mission to use it was 84 days, which is significantly shorter than anything we're talking about for settlement. And I actually had a hard time finding any real data on the atmosphere's effects on the crew. So this atmosphere is basically an unknown. The crew did complain that sound didn't travel well. And the Skylab astronauts stated that a loud speaking voice could only be heard 5 feet away. And the constant shouting required to communicate often left them hoarse. And they mentioned that their cough mechanism was much less effective. And these are annoyances if you have to deal with them for a couple of months. But if you have to deal with them your entire life, that's another story. So, primary advantage of using a one standard lunar Homestead atmosphere is that we have multi-generational data on many millions of people living with this atmosphere, pressure, and composition. We can easily simulate this atmosphere by simply moving our research to Quito, Ecuador, or any place at a similar altitude. And we know that it works. There have been many humans and other life forms and plants that have born, grown, and died in this environment. And don't quickly discount this. There's a lot of stuff we don't know about settling the moon. Not adding the habitat atmosphere to the list is a huge win. And there aren't any significant physiological disadvantages. Sure, the settlers coming from Earth will have to spend a few days gradually adjusting to the reduced pressure, but they can do that on Earth before they leave, or they can do it on the ship taking them to the moon. Okay, figuring out the why and how of fire is a science all in itself, and I don't profess to understand it very well. So I'm going to keep this simple. Here's what we need to know. There are 3 components needed to start and maintain a fire: a heat source, a fuel source, and an oxidizing agent. And oxygen is, not surprisingly, an oxidizing agent. For all the combustible gases and vapors, the limits of flammability are determined by the percentage of dilutant gas and the partial pressure of oxygen. Generally, either increasing the partial pressure of oxygen or decreasing the amount of buffer gas increases the fire risk and the range of explosion limits. Oxygen concentration by volume percent is the primary driver for fire risk, followed by total pressure. That's one of the main reasons why the Apollo 1 fire was so deadly. They used 100% oxygen atmosphere at sea level pressure inside that cabin, and all it needed was a spark. And even at lower pressures, 100% oxygen atmospheres still have a higher fire risk than atmospheres with buffer gases. Basically, increasing the oxygen content over 21%, which is what we're all breathing right now, increases the risk of fire inside the habitat. Reducing the pressure helps somewhat, but the overall fire risk still increases. That's why the Apollo and Skylab atmospheres are just too much of a fire risk to use for long-term settlement. Interestingly, the 1 SLHA presents less of a fire risk. We keep the oxygen concentration the same as on Earth, but we reduce the pressure slightly. The result is that it'll be harder to start and maintain a fire, which also means that we're probably not going to use open fires for cooking or anything. The logistical concerns basically cover how much stuff needs to be shipped from Earth. Obviously, settlements will need to be as self-sufficient as possible. Having to ship stuff from Earth is expensive, and it leaves the settlement vulnerable to supply disruptions. This is where some people get very excited about 100% oxygen atmospheres. The moon is about 45% oxygen by weight. So there is plenty of oxygen on the moon. Sure, it's bound up as metal and other oxides that require a lot of energy and technology to separate, but that's a whole nother issue. Settlements running a pure oxygen atmosphere wouldn't have to ship any nitrogen from Earth, at least not as a buffer gas. They probably will for other industrial processes in agriculture, but that takes care of a big logistical concern. The problem is that the moon has very little nitrogen, at least based on what we found so far. The Lunar Sourcebook states that nitrogen concentrations in mature lunar soils are about 50 micrograms per gram, with some soils exceeding 100 micrograms per gram. That means for every gram of lunar soil, we might find 0.00005 to 0.0001 grams of nitrogen. And we're not even sure about those numbers because many of the lunar samples were contaminated by Earth's atmosphere before they could be tested. It seems that when they were collecting samples, the regolith dust compromised the seals. And by the time they got it back to Earth, Earth's atmosphere had already penetrated the sample containers. So we really don't know how much nitrogen we can find in the lunar regolith. And this is only for the topmost layer of regolith, because the nitrogen has been implanted by the solar wind and Earth's atmosphere. Digging down into the regolith isn't going to help us find more nitrogen. So settlers would have to scrape off huge areas of the moon's surface in their hunt for volatiles. This presents engineering and political challenges. So just for fun, I calculated how much regolith settlers would need to process. A cubic meter of the stuff we're breathing right now has 906.07 grams of nitrogen. A one standard lunar Homestead atmosphere would need 626.15 grams, and a Skylab mix would need 102.42 grams. So let's be generous and put nitrogen concentration in lunar regolith at 100 micrograms per gram. Let's see how much regolith had to be moved and processed to get enough nitrogen for a cubic meter. So that's a tremendous amount of regolith for a single cubic meter of buffer gas. Now, maybe a mature settlement much further in the future could do it, but I really doubt any kind of early settlement could move that much regolith to provide for their nitrogen needs. And like I said, going deep isn't an option. You can start to see how big of an operation the settlement must have if they want to extract nitrogen from the moon. And lunar ice might be a more viable option. However, we have almost no data on the lunar ice. And we don't have any experience operating in permanently shadowed regions. There's a lot of unknowns and a lot of questions, and it's going to take us a long time to conduct all the exploration, research, and engineering needed to extract nitrogen from lunar ice. Okay, so what about other buffer gases? We don't have to use nitrogen. Surely the moon has something in abundance that we could use. Well, unfortunately, it doesn't. We've only found trace amounts of inert gases on the moon. That doesn't mean they aren't there. It just means we shouldn't count on them. And each of these gases comes with their own list of known problems. And that's just for very short-term exposure. Again, we have no long-term data for breathing any of these gases. But I've breathed heliox, helium and oxygen, and it is very uncomfortable. So I can't imagine doing it for decades or the rest of my life. And we could theoretically combine whatever gases we scavenge to make some kind of complex buffer gas mix. But that seems pretty reckless since we don't know the consequences of even one gas, let alone some random mixture of gases. And the engineering needed to extract, process, transport, store, monitor, filter multiple life support gases becomes very daunting. So the obvious solution is to ship nitrogen from Earth. We're most likely shipping nitrogen anyway for agriculture. Nitrogen is one of the basic elements found in all living matter on Earth. Our tissues are built with nitrogen. Most of our edible plants need nitrogen in some way. It's highly unlikely a single settlement would be able to supply its overall nitrogen needs from the moon anyway. Forget about multiple settlements. So ammonia is the answer. Hydrogen and nitrogen. Settlers need the hydrogen anyway for water and other stuff. Its boiling point is only negative 33.34 degrees Celsius, so it's pretty easy to store and transport as a liquid, at least compared to cryogenic stuff. And settlers will probably need to import carbon and other rare resources as well, so we're going to have to figure out how to transport bulk resources anyway. Which kind of stinks because it's looking like real self-sufficiency isn't going to be possible with lunar settlements. They are probably always going to need to bring in nitrogen and other stuff from somewhere else. Okay, this is all interesting stuff. But there is one fact that overrides all of this, and really should be the only factor in determining the breathing gas for any off-Earth settlement. Any breathing gas outside of the narrow parameters of 64 kPa to 101.325 kPa, with a 78% nitrogen, 21% oxygen composition, turns the settlement into a huge, uncontrolled experiment with massive and unknowable consequences. Humans and all of our agricultural plants have evolved to thrive in this very narrow pressure range and in this very specific gas composition. Almost all of our data, especially the long-term data, was collected within this environment. And I'm talking humans, plants, animals, material science, engineering, you name it. We've got almost nothing for the long-term effect of an exotic atmosphere on anything. And if we deviate from this, a lot of our data goes out the window, and we have to start from scratch. And I can't even guess at how much time it would take to get back up to speed. And not only is it, in my opinion, rather immoral to just say, let the settlers deal with it when it comes to all the unknowns associated with an exotic atmosphere, I honestly don't think we're going to get a whole lot of eager volunteers, especially people planning on having children, which a real settlement has to have. A dangerous frontier is one thing. Deliberately subjecting your children to a potentially damaging air their entire lives is another. And 64 kPa, in my opinion, is pushing it. Not only do we have even less long-term data for this pressure, but it also gives the settlements less of a safety margin if they experience some kind of depressurization. They'll just have less time to react if something goes wrong. A one standard lunar Homestead atmosphere, I think, is the best compromise. It's a gas mix that we are evolved for, and it is well understood. All of our agriculture is evolved for it as well. Millions of people are living right now with this atmospheric pressure and composition. We know it works. It's slightly safer fire-wise than sea level pressure, and a whole lot safer than any pressure or any atmosphere that cranks up the percent of oxygen. And it requires significantly less nitrogen than an Earth standard atmosphere. Sure, it still requires a lot of nitrogen, however, but all settlements are going to have to import rare resources from somewhere. Luna just doesn't have some of the stuff we need in the amounts that we need. Probably not even the lunar ice. And on a final note, habitats and life support equipment should be designed so settlers have the option of changing their gas composition and pressure. Maybe they're okay with experimenting on themselves and their children, or maybe a situation forces them to change, or whatever. But the gear needs to be designed from the start to be adaptable so our settlers can be adaptable. This also provides the added bonus of shortening the timeline for lunar settlement. Using a 1 SLHA atmosphere with adaptable gear lets us start establishing settlements as soon as possible without having to do all the research needed for an exotic atmosphere beforehand. We can set up the settlements now and let them do the research when and if they feel like it. All right, here are the resources I used. This presentation is being recorded, so we'll just move on. And that's it. You can learn more about this topic on the Lunar Homestead website. The link to that specific page is at the bottom. All right.
We have
Thanks, everyone.
And we have a couple of questions. So let's start with Frida.
Thank you. That was a very interesting talk. And I'm asked the question, have you considered the gas solubilities in water? I presume that if we're going to have an agricultural and a waste processing system, that we're going to have a fairly large water reservoir, and the gas solubilities may be very important.
I have not considered that, but I imagine since we're using, a composition that we've used for all of our science, it would probably be about the same, maybe a little bit different because of the pressure, but nothing weird like if we used a different composition or an extreme pressure.
Okay, we've done some research on aquatic systems, enclosed ecological systems, and find some carbon-nitrogen relationships that were unexpected. Would be happy to correspond with you.
Okay, yeah, great. I have no idea about carbon-nitrogen interactions with this. My reason for this was I wanted to start working on habitat design. And the first part is, what does that habitat have to contain? The atmospheric pressure and composition.
Thank
you. I would be interested in that too, Frida. Okay. Sounds interesting. Sounds good. We have another hand, Marufa.
Yes. Have you done any research like we have on the Mars Desert Research Station habitats, and we have biosphere too? So what would be the differences if we want to build this type of sealed habitat on the moon? Like what do we have to look at?
I'm sorry, I didn't quite catch it. What was the question again?
Sorry, I think my headphone doesn't work. I'll repeat again. So the habitats we have at the Mars Desert Research Station, also in biosphere too. So what would be the difference if we make similar type habitats on the moon?
Well, I mean, Mars Desert Research Station is effectively at sea level and a little bit higher. So it's basically got a sea level pressure. Biosphere 2 is in the desert. It's about the same too. I mean, Biosphere 2 didn't change atmosphere pressure or composition as far as I know. So it basically any data generated by those analogs would be the same as for at a one standard lunar homestead atmosphere, except for some minor changes because of the pressure. I mean, the only real difference between living in Biosphere 2 and living in Quito, Ecuador is some of your recipes aren't going to work because the pressure's less. That's about it.
I see. And for breathing?
For breathing?
Yes. Oxygen and nitrogen?
Yeah, I mean, it's basically the same oxygen. It's exactly the same oxygen nitrogen mix that you're breathing right now. So, yeah, I mean, the pressure's a little less, so you'll want to acclimate over a couple of days. And like I said, we could either have settlers acclimate in a facility on Earth and then go, or they can dial down the pressure on the ship that takes them to the moon. And after a couple of days, you acclimate to the new pressure. And I've been to Quito, Ecuador, and I didn't have any problem breathing, and most people don't.
And thank you. And we have a question from Jason. Maybe a bit more of a comment. Is there much of a chance for finding a comet with some quantity of nitrogen and to mine and bring that to the moon?
I would say there's a chance for anything. I mean, we've only visited literally a handful of sites, and we've only sampled less than 2 meters deep. And so, yeah, I mean, maybe I would imagine anything volatile that hit the moon vaporized and lost most of it back into space. But
no, I think he's meaning to go bring a comet back from wherever to the moon.
Bring a comet. Well, I mean, my personal thing is, people mess up, and I don't want anybody messing up orbital trajectories when they're bringing a big rock into Earth orbit. So maybe not, but nitrogen's got to come from somewhere. It can come from the Earth. It can come from somebody mining a comet or an asteroid. It could come from, the main asteroid belt. But the reality is that there's not enough nitrogen and other critical volatiles on the moon to sustain a large human presence. So they're going to get it from somewhere. And the Earth is just right next door. So the economics of mining nitrogen is going to be pretty tough if you're not just shipping it from Earth.
Comment from Keith Garrett. I suppose you could have high pressure rooms, 1 atmosphere in hospitals and such.
You could. I mean, there's actually a whole field of science that uses hyperbarics as a way to accelerate healing, but I wouldn't pressurize the whole room. I just have a pressure chamber. That's what we do now. We don't pressurize whole rooms. We just put a patient into a pressure chamber. But it may not even be necessary. I don't know if they have hospitals in Quito when people survive, so it may not even be necessary to crank it up to sea level.
Yeah.
That's the advantage of using this pressure and gas composition is we've got lots of data on millions of people over a long period of time. You change the composition by a couple percentages and it all becomes an unknown.
Yep. Now you have 1 minute left of your time, and the question is, what is the idea behind Lunar Homestead?
The idea behind Lunar Homestead is that we have been waiting for governments and industry and whatever to get us settlements on the moon. And my theory is that it's going to take what it's always taken, groups of individuals with the right technology to go into the frontier and carve out their homes. And so that's what I'm working on, is figuring out the technology and the techniques that will allow groups to go do it instead of waiting for governments or industry to go do it. There's a whole bunch of that stuff on the Lunar Homestead website. You could read all about it.
Yeah, that's a good answer. Go look at Lunar Homestead website. And thank you. That was the egg timer for your presentation ending.
All right. Thanks, Nicholas.
Thank you, Ben. So we proceed to the next.